Is it 2018 already? Postdoc, the New Orleans ACS meeting is coming up. I need data. Again. Yeah, I got a little bit of data to present, but I really need some new equipment. New equipment. Well, time to make it rain.
Damn. Yeah. Yeah. Yeah.
Woo! Nice. This is awesome. You have no excuses now.
Yeah. Yeah.
Everybody, hello and welcome. Welcome to another edition of Ask Us Anything About Electrochemistry. I am your host today. I'm Dr. Neil Spinner. I'm an electrochemical engineer with Pine Research. We are a company based in the United States, and we manufacture electrochemistry research equipment, software, all kinds of different online digital resources as well, including this live stream that you are joining me for. I appreciate everybody who tunes into these. We've been doing these live streams for about a year or so now. This is episode 50 something, if I recall correctly. And the reason that we have been doing these live streams, just to give you a few notes at the top here before I start answering any questions that you have, which you can type into the chat anytime. If you're watching on YouTube or on Twitter, you can type in any questions and I'll get to them as soon as I can. But as a company that manufactures research equipment, specifically in the field of electrochemistry, we get a lot of questions. We get a lot of inquiries and technical kinds of questions from customers pretty frequently about how to troubleshoot different things. And often there is, from our perspective, a lot of questions that are hard to answer through email or over the phone. And so we started this live stream as a way to try to reach out, let the community reach out to us as well to answer questions, related to electrochemistry, fundamental questions, specific research questions, whatever the case may be. As a way for us to communicate directly with you in the electrochemistry community, and particularly for those who might be, let's say, in graduate school or as a postdoc, and they just have some questions that you might feel maybe hard to ask to your academic advisor or to any other people in your lab. We want to be a resource for the community in that way. From our experience with these live streams, there are two sort of extremes of questions to which I would encourage you might avoid and try to find something in the middle. And so the first extreme is something extremely general, like what is electrochemistry or why is the sky blue? Those are perhaps a bit too general of a question and might not serve the purpose of this live stream very well. And so I would discourage questions that are that broad from being asked. The other extreme is something that's so specific that, if you're asking what is the exact activation energy in kilojoules per mole of an iron 3 oxide complex that is reduced in this specific media, like, unless I happened to do my PhD on that exact topic, I'm probably not going to know the answer. And certainly some literature study could help reveal some of those answers, but I would, you're welcome to ask any question that you like, of course. But again, if it's so specific, it's probably unlikely that I'm going to know the answer. And so something in between that is usually helpful, and I'll certainly do my best to answer any of those inquiries that you might have. I'll apologize in advance if anybody's name is mispronounced. We'll certainly do my best to get those correct when possible. And I will run this live stream today for up to about 2 hours, depending on how many questions there are. And I'll answer them as quickly as I can, of course, keeping in mind that it's electrochemistry, and so sometimes the answer to a question can take a little bit of time. And so if you do ask a question, please know that I will see it, and I'll get to it as quickly as I can. If you're watching this live stream after the fact, and you're watching the recording and not live, thank you very much. We appreciate it. If you have questions, you can either try to join a subsequent live stream if you want to ask live. We do this every Friday when possible at 1 p.m. Eastern United States time. So I know it's not always convenient for everybody in every time zone, but if you're able to join us at that time live, you can ask that question. You can also leave a comment on the YouTube video and we'll answer it that way as well, or possibly during a future live stream, and you can watch that next video to get the answer to the question you asked previously. Okay, so I hope that covers all of the logistical things. My colleague and trusty sidekick, or I suppose I'm more his sidekick, but Alex Paroff is not with me today. He is traveling this week, and so I'm running solo, so I'll do my best in his absence. It looks like there's a few questions I can get to right off the top here from Zaki. Zaki says, hello, I'm doing some electrodeposition in aqueous solution at a certain cathodic potential. The electrochemical reaction is diffusion limited. Sounds about right. I performed EIS at regular intervals throughout the deposition period, the DC being the deposition potential, which is cathodic to open circuit. Okay, that makes sense. My system is static, right? You're not rotating, no RDE or RCE. Okay. And the question is, can I model the EIS spectra with some equivalent circuit? Most probably yes, is the general answer to that question. How well will the fit be, right? Which Warburg element, if you must use one, should I use? How can I extract useful information from those spectra? Okay. Can you model the EIS spectra with an equivalent circuit? Most likely, the answer to that question is most likely, with the exception that if you determine the EIS data are not valid, then the answer would be no. And so I'll try to answer or spend the time, at least the bulk of my answer, answering the last part and talking about Warburg elements and how to extract something from them. The answer to the first part of your question involves the use of what are called Kramers-Kronig relations or analysis. I'm not going to get into that as heavily just for time, but if you did have questions about how those work, I can certainly show you some slides or some information about Kramers-Kronig if you like. Effectively, Kramers-Kronig is a transform. It looks like a circuit fit. It acts like a circuit fit, but it's really just somewhat of a binary, is my data good or bad kind of an answer. And so if you're getting EIS spectra at all these intervals, what you want to do before you consider any circuit fit or any model or anything like that is to run Kramers-Kronig on each of those spectra. And if the Kramers-Kronig comes back with a relatively good adherence to your data, basically what that means is that, yes, you can move forward to determining an appropriate equivalent circuit. Now, what that circuit is, of course, is subjective. The shape of your data will likely determine and, for the most part, guide you to which specific equivalent circuit you should pick. So, for instance, the most general case being any semicircles typically are represented with a Randall's element, which is a resistor and a capacitor, or a resistor and a CPE in parallel. Warburg elements, as you noted, are typically observed at lower frequencies, so to the right of your Nyquist plot or to the left on your Bode plot. And there's generally two types of Warburg behavior that you can observe: infinite and finite. So let me try to go through a little bit of the differences between those and what they look like, just to answer, to address your inquiry here. Let me share share my screen here. I have some slides from one of my EIS webinars. So let's see if this gets here. So I'm going to hide the question so you can see. So for Warburg, infinite Warburg, what you would likely see, I'm just going to move some of this stuff out of the way and just sort of focus on, is something like this, right? So first of all, Kramers-Kronig determines your data is good, right? You're trying to figure out what model to use. Okay. If, for example, you see this kind of tail here, right? This sort of 45-degree tail, might not be exactly 45 degrees, but something like this at low frequency on your Nyquist plot, then that would be an indication of an infinite Warburg, which is usually just seen as a W. Sometimes it's ZW. It depends what software you're using, right? But it will be usually represented that way. Okay, that is an indication of diffusion to an electrode surface through a semi-infinite distance, let's just say. If, for example, instead what you see is what kind of might start out, so the resolution's a little poor here, the beginning of this here is kind of a 45-degree sloping line, but then it sort of curls like a semicircle. This could be a Warburg behavior, which is still diffusional, but it is a finite Warburg diffusional behavior, which would be usually called a Warburg short. Okay, and this is when you have diffusion, but it's through a diffusion layer that is of a set thickness. Okay, so those are graphically what you would see between those two types of Warburg diffusional behaviors with your system. Now, what can you get and extract useful information from those? Well, in either case, you will get W, which is a Warburg coefficient. Again, depending on the software that you're using, this might take a different form. You want to be cautious, mainly because, for instance, from Barden-Faulkner, the textbook in electrochemistry that most people are relatively familiar with, the Warburg coefficient is often described in this way. It's equal to these terms, okay? And so what that means mathematically is that the impedance of a Warburg element is defined this way. Now, the reason this is important only is because it matters what the units are. So when you're trying to extract useful information from a Warburg circuit fit, typically that useful information is the diffusion coefficient. Okay, that's the most fundamental thing that people usually calculate, which comes in the form of this bottom part here, right? This is, again, from Barden-Faulkner's textbook. The Warburg coefficient is usually a function of diffusion coefficients of my species. We typically neglect one of these. This is just kind of the common practice. You can solve for D, for instance, using all of the other pieces of information that we just know is the ideal gas constant, the temperature, the number of electrons transferred, Faraday's constant, the concentration of my analyte, as well as the surface area of my electrode. These are all just known constants. The W comes from my circuit fit, and then I can solve for the diffusion coefficient. So that's usually the quote unquote useful information that you get from a Warburg circuit fit. I just hesitate on this very briefly because the Warburg coefficient will either be defined this way or this way. Okay, so, and sometimes this is like, ZW or Q or something else. Normally with a CPE or a capacitor, the constant, the way the impedance is defined, the constant is in the denominator here, right? I prefer personally, and with my company's software, to put it in the numerator. It's a departure. And just the reason for that is because it makes this equation more direct. Otherwise, all you end up with is 1 over W, right? I'm just mentioning this as a means to make you aware. Pay attention to the unit of the Warburg coefficient you get from your circuit fit. Everybody's software is a little different, and some of them have it flipped compared to the others. So just make sure, because otherwise you'll get a very wrong answer, of course, for your diffusion coefficient if you don't know how this is defined. Okay, that's the first piece of information. Whether you have an infinite or a finite plane Warburg, whether you have this behavior or this behavior, you will get a W from your software when you do a circuit fit, and that from that you can get the diffusion coefficient. The second piece of information that you can get, and then I'll move on to other questions. And again, Zaki, if you have a follow-up, if you wanted me to sort of elaborate on Kramers-Kronig, for instance, I can, time permitting. Please follow up if you need more clarification. If you have this behavior for your Warburg and it's a short, it's a finite diffusional path, then the other piece of useful information that you would be looking to get is the length of that finite path, right? For an infinite Warburg, you're not calculating the length of the diffusion layer because it is infinite, or it's semi-infinite, or it's large compared to the size of my electrode. And so that's not a piece of information that you're looking to calculate. On the other hand, when you do a finite Warburg short, for instance, we have the second parameter. Again, it depends on what software you're using. We call it B. Some other places, there's a different, I don't know if they use E or they use sigma or something. You'll see this defined in software differently. So again, just be aware of the unit, be aware of the variable. Usually with a Warburg short, there's a second fitted element that is, I'm calling B. And you can see the definition of B involves the diffusion coefficient as well as delta. This is the diffusion layer thickness, this delta. And so the two-step process, for instance, if you have a Warburg short, is doing your fit, you get W and you get B. From the W, you calculate the diffusion coefficient. And then from the B, where is it? Here it is. You can plug in the diffusion coefficient here, and you can calculate the thickness of your diffusion layer. Okay, so if you have a Warburg short, the useful information that you can get is twofold, right? It is the diffusion coefficient and the thickness or the length of my diffusion layer. Okay, and again, the shape of your data, provided it is valid from Kramers-Kronig analysis, should ultimately reveal whether the data is valid in the first place and which of those kinds of behavior, short or infinite length, you observe, and which of those Warburg elements you would want to fit. So Zaki, that hopefully answers your question. Please again follow up if you want some additional information or clarification. Okay, Sam Zhang has asked, could you please talk about electrowinning and electroplating? What's the difference? How do copper 2+ deposition in both cases? You know, I'll be honest, electrowinning is a process. I've heard this term, but I don't know it very well. Electrowinning is electroextraction, electrodeposition of metals from their ores that have been put in solution via a process from leaching. Okay, so so it seems like if I were to sort of extend this, leaching again is also something that I haven't done personally, but you know, for example, this is let me think this through. For you know, when we get certain metals from the ground, for instance, when we mine for lithium, cobalt, nickel, whatever, like element from the ground, it usually there's rocks, right? There's some sort of material, and it's not just pure elemental material that we're looking for, right? And so to get that material in its pure form, you have to do things like leaching and perhaps this electrowinning process where you might take like some material, some rock that has a variety of different elements in it, and you can use electrochemistry to preferentially extract a certain material. So for instance, I want to see for example, a standard, I'm just looking at the reduction potentials for copper. So copper 2+. So for instance, let me share this, like this is just a Wikipedia page. So you can see, for instance, let me hide this here. Actually happens to have the copper, information front and center here. So like the standard potentials for various copper depositions here, just for instance, copper 2+ going to elemental copper, copper 2+ going to elemental copper. Sorry, I had it highlighted. I'm trying not to. Is plus 337. Okay, so what this means, this middle one here, right? Effectively what that means is if I have a potentiostat and I set the potential less than plus 337 millivolts, I would run this reaction would have a driving force to run. But let's just say I had some other material in solution, right? That let's just find one just as an example. Let's say here's one. Here's tin. Okay, so let's say I had a rock that has tin and copper. I'm just making this up, right? But I think the concept is roughly accurate. Okay, so sorry, I'm trying to find it again. Where did I have? I had it highlighted, didn't I? There it is. Okay, so for example, the tin, the reduction of tin 2+ to solid tin is minus 0.13. So what this means is, for example, if I had copper in solution and I had tin in solution, if I am negative of the copper but positive of the tin, copper will like plate, but tin won't. So like this is probably in some ways related to, or an answer to your question about like electrodeposition and this whole process, is that you're carefully selecting potentials where the material you're looking to deposit, which is usually something like this, it might not be exactly this equation, but something similar where you have ions that go to solid onto some surface, right? You have to apply a potential, because it's usually a reduction, that is at or less than the standard potential for that process. But if you don't want to deposit some other material, you have to pick a potential that's above that one so that it keeps, you can keep tin in the 2+ while you make sure you deposit copper to elemental copper. So that's just a general example. That would be if you had these ions all in solution. You could do the exact opposite sort of theory if you're going the other direction. Like I said, if you have a rock and it's solid, you're trying to make it into ions. Again, I think that is possibly the electrowinning, this leaching, this sort of idea. You're getting a raw material with a bunch of elements. You're trying to like extract some of them. That can usually mean getting from the solid to the ion. And so now it's the opposite. You're trying to increase the potential so that you oxidize to a 2+ species or something like that. And you can carefully select a potential that oxidizes one thing but not the other. I think your other part was how do the copper 2+ deposition, how does it run in both cases? So again, it's somewhat related to the point I'm making. If you have, let me try to put it this way. If you have a solution of just copper sulfate or copper nitrate, right? Like you're doing an electrodeposition of copper onto platinum. This is a very common kind of a electrochemical process. And you prepare your electrolyte and you have like 0.5 molar copper sulfate in a platinum electrode in solution. Well, if you go negative potential, right, based on the chart I said it's like 300 millivolts. Let's just say you apply 0 volts versus NHE. You will start plating copper. But there's nothing else in solution. So I could apply minus 500 millivolts. I could apply minus 1 volt. I could apply minus a million volts. I'm exaggerating. But the point is that you have only one ion or metal in solution that you're trying to deposit. And so a lot of times with an electroplating or an electrodeposition kind of a process, it's a very controlled, specifically guided electrochemistry process where you're providing the ion of interest. And in doing so, you can actually more carefully control the deposition process of, for example, copper 2+ to copper, elemental copper, because the amount of current that you generate is pretty heavily correlated with the amount of copper formed, like physical film of copper. And so you can correlate that a little more easily. You might have some side reactions. You might have some double layer capacitance and some things that are eating at the current, but it's just copper. On the other hand, in this electrowinning, again, if I'm understanding it correctly, which is possible, I've misunderstood it a little bit. In a leaching process or a deposition where there's a lot of other metals present, that isn't always the case, right? Because you could have interference from other deposition. If you have copper, but you have tin and you have zinc and you have all these other metals, you're going to need to be careful because the film you form might not be pure copper. It might be an alloy. It might have other metals. It depends on what potential you pick. It probably requires a little more, care in the potential that you select, and that would probably impact the film that you get as well. So that's the best that I can sort of try to describe those processes, again, without any specific data. I don't have any electrodeposition data in front of me, I suppose, but hopefully that's a relatively clear, concise explanation of electrodeposition or electroplating there. Reactive has a question: what's a good way to explain or define battery voltage ramp up if you're asked about it? And you said Thevenin model. Is that? I'm not familiar with Thevenin. Describes the fixed parameters in the classic model as variables, the state of charge and temperature. This one I'm not. Thevenin's theorem. Any linear electrical network containing only voltage sources, current sources, and resistances can be replaced at terminals A to B by an equivalent combination of voltage source in series with a resistance. I think this is like a simplification of the circuit. So that one, I don't know that I have a lot of insight to provide to you. I don't know this model very well to comment on it, but a good way to explain or define battery voltage ramp up. So if you're talking about battery voltage ramp up, that's a charging process, as best I can surmise from your question here. Explain or define battery voltage ramp. I mean, I guess I'm not sure what kind of explanation is needed. So like if someone is asking, why is the voltage of a battery increasing? My battery voltage ramp up. The short answer is that it's being charged. That feels like too simple an answer to me. I wonder if maybe there's something I'm not fully understanding about your question or about what you're maybe being asked. You said, if you're asked about it. So is someone asking you a specific question? You know, again, it's like a battery specifically operates between two voltages, right? Representing the maximum amount of energy it can deliver and the minimum amount of energy once it's delivered all of its charge. And between those two voltages, like for lithium or for sodium ion, whatever the type of battery you're working with, usually indicates the ion of interest is fully loaded in one side or the other. So for example, when a battery is discharged, if it's a lithium battery, for instance, physically what that means is the cathode is loaded up with the lithium ions and the anode has no lithium ions. And so one way to answer or think this through is okay, why? I'll finish that thought in a moment. Why doesn't increase instantly but takes time? Right. Okay. This is a really hard thing to answer. I have a hard time describing this. I'll do my best to try to answer this. It is screen. I'm gonna share something with you. I'll try to answer this question as best I can. Okay, so what I think you're describing or referring to with your question is let me get to draw for you. So for a charge discharge, right? If this is let's just say this is capacity and this is voltage, right? So when you're charging a battery, it usually does this, right? And so what you're probably referring to is this region here. And so between here and here, for the most part, the voltage takes a long time, right? This capacity on the x-axis is time, and it takes a long time unless you're charging really, really fast. But the voltage is not increasing very much, right? It's like it goes from here, right, to here. It's like this is not a very big span of voltages compared to the actual limits of the battery itself. And so why doesn't it change very much? The real answer to your question is thermodynamics. It's a very tough thing to think through. I'll try to explain, and I'm going to draw it. I might draw it poorly, so apologies in advance. The voltage of a battery, right, of any cell, when you start charging, it takes some seconds before going from OCV to charging voltage. You start charging. It takes some seconds before going from OCV. Oh, that sounds like that sounds more like an equipment thing. If you have a battery at OCV, and then you you start charging it, or you tell your battery cycler or your potentiostat to start charging, but it doesn't go right away, that is probably an equipment thing. The software or the battery cycler has some sort of a resting period before it starts applying. If you have a battery at OCV and then you start putting current into it, the voltage will change instantly. So if you're not observing that, then there's something with your equipment that's probably getting in the way. The Thevenin model has capacitors in it. Right, so it's a resistor capacitor sort of a model. Capacitors can slow things down. So if you do have capacitances or heavy capacitive elements, that will slow things down as well in general, as well as the response of your potentiostat. So I don't know if that has something to do with the phenomenon that you're observing. But I will just finish this one thought because again, I don't know if it's completely what you're talking about, but just as it relates to the voltage you're seeing, just so I can finish this idea, if it's helpful for you or for anybody. The E of my battery, basically, at any moment in time, this is true of fuel cells as well, in most 2-electrode systems, it's E cathode minus E anode. Okay, so sorry, that A looked really bad. I want to do it again. Okay, so whatever the individual voltage is at the cathode and the individual voltage of the anode, the difference of those two at any moment in time is the voltage of my battery itself. This red curve that you see is at all times this difference. And so this right here, this voltage is at 0% state of charge, right? This over here is at 100% state of charge, all right? And so, as I said, at 0% state of charge, I'll just use lithium because that's what I'm most familiar with. At 0% state of charge, the cathode has 100% lithium, and the anode has 0% lithium in it. It's the opposite at 100% state of charge. So this is state of charge of the battery, of the overall battery, right? State of, that was ugly, 100% state of charge. The cathode at 100% state of charge has no lithium in it. I could say lithium plus, I suppose. It's probably a little more accurate. No lithium ions are in the cathode, right? And when it's fully charged, the anode is fully loaded with lithium. Okay. And the reason that it looks like this is just because the anode and the cathode have different individual profiles for lithium plus percentage, basically, and potential. Lithium plus, okay? And so from 0 to 100% for the lithium plus percentage, and this is where you'll have to take this with a grain of salt. I'm not 100% sure what they really look like, so you'll have to just take this with some grain of salt. For the cathode, let's, for example, at 0% lithium in the cathode, I'm fully charged. And so the voltage is probably highest, okay? And so the voltage at 0% lithium, which is 100% state of charge, is high. And then as I start removing lithium from the cathode, its voltage starts to go down. It does some pattern. On the anode, on the other hand, at 100% lithium, that's when it's fully charged. And you see the E of the battery is at its highest amount, which means that either EC is really big or EA is really small. Because if EA was really big, EC minus EA would be a little number. And so also at 100% lithium percentage, the anode voltage is probably lower. And so actually what you might end up seeing is that you have a similar looking curve for the cathode and the anode. But remember, what we actually sort of have is at 100% state of charge, it's this potential minus this potential, because that's the amount of lithium in each of the respective parts. And so as we're charging our battery, the cathode is moving this way and the anode is moving this way. And again, the exact curves I've just drawn and the values don't focus too much on that, but I hope you can kind of imagine at every point in time, I'm subtracting this number and this number. And it just sort of happens thermodynamically that throughout the bulk of the charge discharge process, one of them is going down, let's just say one of them is going up, or maybe it's the other way around. Maybe this is going up. The difference of the two happens to be about the same number. It's only changing ever so slightly. And it's probably, I've probably drawn this incorrectly, because if one of them was going down and the other was going up, this number would be changing a lot. So actually probably what happens is something like this actually goes down also, or something like that. Something like that probably happens, because the difference of the red curve and the green curve stays almost constant throughout that portion. And so that's why, again, I know that may not be reactive exactly what you were asking, but for anyone else who's interested in battery charging, phenomena, that is for the most part explains why this red curve is flat for a decent portion. Um, that explains it there. And then I guess, yeah, the Thevenin model, the open circuit plus IR. Yeah, I'm neglecting IR drop in this case here. I just sort of talking about anode versus cathode. Again, I can't speak more specifically to this model. I'm not familiar with it. I did just sort of find a little information on it very briefly here, but I can't speak too much more with more knowledge about the Thevenin model or exactly how it relates to batteries. I haven't seen, and it might just be my lack of knowledge for sure, like literature using this model to describe battery behavior. But this was just the one part of what you said that again made me think about, if you're sorry, headphones keep turning off. And put something in the background. Sorry for that. Okay. The point I was making was, if for example your battery is hooked up to your cycler or your potentiostat, and you click, give me, 5 milliamps, I should see the voltage start to rise, but it doesn't rise right away. Something is slowing that down. So either there's some capacitive element, like you said, there's capacitors. I don't know if that has something to do with. There's capacitors in the battery somehow, or there's capacitors in your cell cable of your device, or like with some software, programs, a lot of times what there is like a delay period. So like you click go, apply, a milliamp or something, but there's like a 3-second rest while it sort of figures out what it's doing, and then it starts applying. So it might be that you don't see the voltage going up right away because there's some resting period built in, and you just aren't maybe aware of that. But I think I'll leave it at that for now. Yeah, do follow up, I guess, if there's something I didn't cover quite right. I hope I talked through some of these phenomena for you. Reactive. Okay, Zaki had a follow up. Thank you. I'm a bit concerned about the limitation of my static system. That's fair. How my using a non-rotating system will affect the fit or the spectra, given the KK test validate. That is less of a concern in my estimation. So I think it is certainly possible to be, or let me put it this way. It is reasonable to be concerned that using a static electrode will cause limitations in the electrodeposition. You're doing electrodeposition. Did I remember that right? Yes, electrodeposition. Okay, just reminding myself about your question. In a static system, you might be limited in terms of the quality of film you can get, something like that, because probably the diffusion you're going to experience will be likely the infinite model of the two that I showed you. And the reason for that is that as your electrode is stationary, there is nothing to prevent the diffusion layer on the electrode from just growing. Right? Because if you were to rotate or stir solution or do something to improve the hydrodynamics, you would add convective elements to your electrolyte, which would force reagent to the surface of your electrode, which would do two things. It would potentially reduce the size of the diffusion layer and potentially prevent it from growing over time. And it would also speed up the kinetics because you wouldn't be diffusion limited. Or if you're diffusion limited, it would be with a known thickness of diffusion layer. Okay, you can still be diffusion limited or diffusion controlled, however you want to say it, but having the diffusion layer grow consistently as time proceeds limits the current and the effectiveness of your experiment in a lot of ways. Diffusion is, it's usually a bad thing. It's usually getting in the way of your results. Okay, so from that perspective, it is. I would agree with you about what you would say as a limitation of your system. What I would caution you is if you're doing these tests academically, you're trying to learn something about your system, and it doesn't excuse me, matter maybe the quality of film, but you're just trying to study it. That to me is not as applicable. Um, if you're thinking the EIS data will be poor because my system is static, I would not um, think that way. There's nothing really intrinsic about a static system that should lead you to get poor results. You should still be able to get good results with a static system like Kramers-Kronig validated impedance results. That should still not be a problem. Um, it's just that all the things I just talked about will be the case. You'll have an infinite plane of diffusion. You might have, you know, pretty uh, pretty detrimental diffusion to your film growth, but the impedance results should still be fine, assuming you are able to have your experimental setup be good and all of those sorts of normal trial and error things that you might do with setting up an electrochemistry experiment. Um, I would not do rotating experiments as a means to get better impedance data. I would do rotating experiments as a means to get better film formation. The impedance data, either way, you should be able to analyze just fine. Okay. Is it Ceylon? Ceylon or Sifan? Ceylon, it's an L. Okay. Hi, sir. How to validate data of voltammograms and how to figure out correlation between two data sets. Um, I think it's a little bit general. I guess the question of validate, I don't really know exactly what you mean by validate. Um, and then correlation between two data sets as well. I think I don't know exactly what you mean, right? What are you trying to correlate? If you have two data sets, um, are you trying to, trying to compare something, right? Like maybe, for instance, you have two voltammograms at different scan rates, and you're trying to compare the results. If you're trying to do different kinds of analyses, like peak height of your, if you have a peak and you do different scan rates, you'll get a bigger peak height. You can use some expressions to correlate or calculate parameters based on those kinds of things. As far as validate is concerned, if you're asking, for instance, in the way that I was just describing Kramers-Kronig for impedance data, you can run impedance spectroscopy and then do Kramers-Kronig, and it will tell you if the data is valid, so to speak. There is no such diagnostic tool for voltammetry. That doesn't exist. There is no, Kramers-Kronig for voltammetry, for instance, that you can do a diagnostic to say, is my voltammogram valid? That's not the same. Um, not the same level of analysis, and it's not the same kind of experiment. It doesn't have that sort of binary good or bad, right? Um, validation is not necessarily um, the right terminology, I guess, or a commonly used terminology with a voltammogram. Uh, a voltammogram, if you're doing LSV or CV, for instance, um, is usually being done as a means to explore a uh, a system, a redox system, and you're looking for peaks. You're looking for what happens within a certain potential window. You're looking for the current response to give you how much double layer capacitance you have. It depends if you're looking for a supercapacitor or just a material film. There's a lot of things there, right? What you might have as a I don't even call it validation, but just a tool to determine how your voltammogram looks. For instance, you might have something. I'll draw something for you quick here. Let's say you have a voltammogram, right? And it's something very. This would be like a carbon voltammogram. It would look kind of like this. There's not very much interesting going on, and you have just oxygen evolution and hydrogen evolution. But it's flat. There's nothing interesting going on. And then you run another test with a different electrode or a different system, and you get something that looks like this. I'm exaggerating this so you can tell the difference. Obviously, uh, you see a much bigger um, gap between the positive and the negative scans. It's also tilted, right? You might see this like there's some angle here, it's tilted. That is sort of a visual diagnostic that I have a high resistance. I might have a leakage in my electrode. Um, there's probably a physical problem with it. If you have something that looks really like this, like tilted, or there's a big gap between the positive and negative sweeps, that is, again, not the same as Kramers-Kronig, but there's something there where you would, and even as a comparison to your other point, if you're comparing the red and the green traces here, you might say, well, the green trace, there's something wrong with my electrode, there's something wrong with my system, whereas the red trace is more ideal, something like that. So that's just one example I can give you as, I don't know, a diagnostic. Um, Otherwise, the answer, I suppose, to is my voltammogram valid is more of a one that you would compare your voltammogram with literature results if you're trying to study X, Y, or Z reaction or system, whatever it is. You would compare with someone in the literature. What did they get? And does mine look like that? Those are the typical kinds of comparisons you might do. All right, Ferris, good to see you again. Is asking, is the diffusion coefficient a property of just the electrolyte that you are studying, or does it also depend on the cell construction? For example, would it change with or without a porous separator? The diffusion coefficient is a function, I believe, of the electrolyte. Like the diffusion coefficient, of like chloride or something, is not a function of the cell construction. Um, I believe that is true. The tricky thing, of course, is that you could uh, do multiple tests in different geometries, and you will probably get um, a different diffusion coefficient each time, and that's just because experimentally um, things are very difficult, right, to get consistent results exactly. And so you could do something in like one type of cell and you get a diffusion coefficient. You do a different kind of cell, you'll get a slightly different um, diffusion coefficient. But it's related to the gradient in the concentration. So the it comes from Fick's law. I'm just reading a little about it to try to make sure I describe this accurately. Um, and I do think it's related to the amount of movement in a period of time. And in theory, I don't think it should depend on the vessel that you're using. And with and without a porous separator, the if you're talking about like you have a vessel, like let's just say you have one little vessel filled with electrolyte, right? And then you have a different shaped vessel filled with the same electrolyte, and then you have a membrane cell, and each side is all filled with the same electrolyte, and there's like a separator in between. My my understanding, and I could be wrong, so apologies if I'm understanding the fundamentals wrong here, but my understanding is the diffusion coefficient of the ion in question in those three situations I just described would be the same. Like you have 1 molar whatever of solution, whatever that has a diffusion coefficient associated, because diffusion is like random motion of molecules. It doesn't depend on where it is. It's related to the concentration of the of the solution that you have. So I think that's the case, but again, the problem is, even if that is the case, practically you probably have a hard time observing that, because practically measuring diffusion coefficients can be kind of all over the place. And then it's also possible to, again, just to be fully honest, is that I'm not correct. I might have a bit of a misunderstanding of that. There might be some impact of it, and I probably have to go back to first principles. Like it's fixed. It comes from fixed laws of diffusion, right? Um, and I might be not understanding this properly, but that's what I think is the answer. I think the answer is no, it does not. But I would encourage you to maybe look into fixed law. I might have to do that as well to try to make sure I'm correct, because I might not be. Okay, let's see. FCB has asked, why is the counter electrode and working electrode separated in a different cell? So it's not always. It can be. Mainly the reason why you would want to separate the working and the counter electrode is because the counter electrode in your electrochemistry experiment may be running some redox process. Actually, it is almost certainly running a redox process that you have no idea what it is. Now, that might just be buildup of double layer capacitance, right? Consider that when you're running an electrochemistry experiment and you hook up your working and your counter and your reference electrode in solution, and you tell your potentiostat, do my CV or EIS or bulk electrolysis, whatever you're doing, the current that you're measuring at your working electrode has an equal and opposite current occurring at the counter electrode necessarily. So while the working electrode is in such a way that you, I'd say, can or often should know what is going on there. You have this much milliamps and this many millivolts of potential and current occurring at the working electrode. The working electrode, what's happening, and so you can know where that current is going to. This particular redox reaction, this particular Faraday or non-Faraday response. Those things are not the case on the counter electrode, right? It might be that you can assume, oh, the counter electrode's just doing this process. You don't really know. And part of the reason is that it's the potentiostat's job to give you what you asked for at the working electrode. It's not the potentiostat's job to give you anything in particular at the counter electrode. It's actually, the potentiostat is actually controlling the counter electrode directly and moving it wherever it needs to be to give you what you asked for at the working electrode. And so again, if the counter electrode is doing something, it might be oxidizing something, reducing something, whatever, to be giving this many milliamps, so your working electrode is doing what you asked for. What if the counter electrode is producing some sort of byproduct, right? What if it's inadvertently oxidizing or reducing some species, producing gas, producing some radical, some byproduct, whatever. There could be something happening, but you don't know what it is. Well, if that's happening and its product at the counter electrode works its way to the working electrode, you could have a problem, right? You don't want to have unknown species interacting with your working electrode because it might affect your results. Okay. That situation I just described is not always a problem. Okay. I want to stress that. So in a lot of sort of normal, I'd say, situations where you have small electrodes in a vessel, a beaker, a cell, and you have like nanoamps to microamps of current, relatively low voltages. Most of the time, this is not a problem. Even if the counter electrode is doing something that you don't know what it is, you can just have the counter electrode and the working electrode dipped in solution. And even if the counter electrode is producing some small byproduct, it's probably in such a small amount that it's not going to impact your working electrode at all and your results. However, because it can be the case that that is a problem. For example, people do electrolysis in separated cells. This might be what you're referring to. And in the case where you have that situation, you're providing a lot of potential or a lot of current to the working electrode because you're trying to generate a product. You're trying to create gas to send to your GC or your MS, whatever the case may be. The counter electrode in that case might have a very large opposite potential or current and be doing some crazy thing. So in that way, we put a frit in between the working and the counter electrodes, either through a separated cell that has a frit in between, or we have one vessel and we have our working electrode in there and our counter electrode, but we put the counter electrode in its own isolation tube. So there's like a barrier, there's a frit. The frit still allows diffusion because there has to be ionic communication between the working and the counter electrode in solution. If there's not, you could run into a compliance voltage issue. You could run into other issues. But what it means is that if you're generating some crazy thing at your counter electrode, well, it stays relatively contained. And some of it might diffuse through this frit, this extra containment, and make its way to the working electrode, but probably a much smaller amount, and it won't cause any issues. Usually that's the reason that we separate if we do at all. Um, I also just the last thing I'll say is that one of the things I mentioned was for a lot of normal systems, this is not a problem. And so in a lot of those cases where it is not an issue because nothing at the counter electrode is going to interfere with your working electrode, it is probably better to not use an isolation tube, to not separate them. Because adding a frit or an extra kind of isolation when it's not needed is probably only going to cause problems rather than solve anything, because the frit could become blocked. You might not have enough solution in the extra compartment. You could have no current passing. You could create a compliance voltage issue because of added impedance. There's a lot of problems that can occur by isolating your counter electrode if you don't need to. So I just want to have you exercise caution. Only isolate the counter electrode if you do suspect that the counter electrode's unknown reactions could cause an unwanted side effect. Otherwise, I don't recommend it necessarily. Okay, let's see. I'm not sure what this comment or question is. The free energy is possible. What do you think about this? I'm not sure what that person. Free energy. John Bedini. So I don't I don't have any knowledge of this. This is a free energy something. I'm sorry, Dennis, I don't know who this person is or what this question is about. I'm gonna have to skip on this. I'm very sorry, but I don't know anything about this or who this person is. So Ceylon has clarified with this comparing two data sets of square wave voltammograms to see the difference. Okay. So if you're doing square wave voltammetry, yeah, square wave voltammetry is a tricky one because it's like all trial and error, right? For those who are not maybe aware, square wave voltammetry. Actually, yeah, let me do a thing here instead. Oops, that's not what I wanted. Sorry, give me a moment. I want to pull up. I'm gonna pull up the waveform. Square wave voltammetry. We have a nice illustration of it, so I'm just pulling this up for you. So sorry for a bit of the delay. Square wave voltammetry. Let me hide the question so I can kind of zoom in. So the square wave voltammogram looks like this. It's like a voltammogram. You're going from one starting point to another starting point, but you're going in a square. So you go up a little, down a little, up a little, down a little. Okay. And the parameters involved. Where was I? You can see some of them here, for instance. The all of this is like a trial and error, right? So how far you go up, how far you go down, and how much you increment the baseline each time. These are all trial and error things. And so square wave has the benefit often, let's see if we have a voltammeter, of clarifying a peak location. So for example, this example here shows when you scan both directions, you get the same peak location. Whereas if you do it with cyclic voltammetry, the peaks will be split by 60 millivolts ideally. Square wave voltammetry has a way of clarifying the peak location because it's subtracting the background current, and the background current often is. I'm getting into a lot of concepts here, but effectively the background current or the peak, the way a peak forms in a voltammogram is a result of kinetics and diffusion interplay. And the way that works is that when you're scanning in one direction or another, you get basically a different measure of the peak. With square wave, you can see that these two sides are both about zero because I'm subtracting the background. And so I go up a little, I go down a little. So it's kind of like removing the double layer capacitance or the non-Faradaic aspect of my voltammogram to like further clarify the E0, the standard potential of my reaction, as well as the peak, the amount of current associated with that. Now the trial and error really comes into play from the perspective that if you go up and down and you increment the baseline each time. So if you want to, if you go too high up or too high down, the background you're subtracting is no longer related anymore. Like if you were to go up like 100 millivolts and down 100 millivolts, it's like the up jump and the down jump. The down is the background, the up is the like induced reaction. If this is so far away from this background is no longer related to this process. Like if I'm shooting up by a whole bunch of millivolts and then I'm going down, this is no longer the background related to this. Like you might be way over in this peak and I'm at this other end of the voltammogram. So this is what I mean by the trial and error is that comparing them by adjusting a little bit at a time, like increment by 10 millivolts, and increment by 20 millivolts, increment by 15 millivolts. Okay, and see how that clarifies the peaks that you get or something like that. If you start to see odd behavior where you don't have a zero baseline maybe, or you don't get a peak at all, that would be something where you would perhaps draw the conclusion that my parameters are off. I'm jumping too high, or my increment is too large, or I'm not jumping high enough. Something like that. Without getting into more specific data sets, I guess that's sort of a general advice I think I would offer for this. But square wave voltammetry fundamentally is really a trial and error kind of a thing. It's a very powerful technique because of its subtractive nature. You're subtracting a background current actively. Pulse techniques have that benefit. The downside is that it's not always easy to know exactly what the parameters should be. And so there's just a lot of trial and error involved. Okay, let's see. I am down to another question from Reactive here. What are advantages of hydrogen energy storage to lithium battery storage? How to justify comparing them for a solar photovoltaic park 2 megawatts? Interesting. So it's a good question. I don't know if I can speak perfectly to all of it. Um, the storage is one thing, and then the application of the power system is another. So, for example, if you're talking about hydrogen energy storage compared to lithium battery storage, the hydrogen energy storage is presumably using a fuel cell, right? So the if you're looking at a 2 megawatt system, right, of power delivery, that could be a really big battery, or basically a set of batteries, or a really big fuel cell or set of fuel cells, like a stack, right? And the fuel cell would have stored hydrogen tanks or compartments of some sort, right? To eventually, send through the fuel cell to get the power as needed. And the batteries require no storage of like external storage. So like a battery is all self-contained, right? The lithium storage, so to speak, is all internal. It's all there. A fuel cell is like a system, and then you have this extra stored tank of hydrogen and oxygen, unless you use air. Extra stored containers. So one of the disadvantages of the fuel cell is that you have to have this extra storage of compressed hydrogen gas, for instance, and there's just a danger associated with that, right? Hydrogen is tremendously flammable, and those, there's safety concerns related to that, of course. We all use petrol or gasoline in cars, and gasoline is flammable. So I don't want to overreact to the danger. Hydrogen is just like anything else. It's a flammable gas. When it's compressed and stored, there's a risk or a safety associated with that. Batteries certainly have their own safety risks as well. Lithium is flammable as a metal. It can't be exposed to moisture and air. So one of the disadvantages of a lithium compared to a fuel cell is that a fuel cell is more atmosphere tolerant, whereas a battery is not. And a battery is not really, it has to be very well sealed and contained, whereas a fuel cell operates usually on oxygen or air, and so it can obviously be exposed to the elements a little more easily without running into problems. And then, the justification, if you're looking at one or the other, to the best of my knowledge, a fuel cell or a hydrogen storage system is going to be better at delivering a lot of power. A battery system is probably better at delivering a more steady or slow amount of energy over a longer period of time than a fuel cell is. Now, that's not to say that you can't get a lot of power from a battery as well. We have like electric cars that run entirely on batteries, and you have to accelerate very fast, so you need a lot of power very quickly, and batteries can deliver that too. But generally speaking, batteries are a little less equipped, generally speaking, at delivering very fast amounts of energy. And the reason is that is effectively a discharge, right? When you're delivering power or energy from a battery, is you discharge like a lot of current very quickly, and batteries do not always respond very well to that situation. You increase the risk of a failure event or a thermal runaway, or at the very least, a more rapid degradation of the battery itself. Fast charging and discharging diminishes the life of the battery. As an example, most of us probably have phones, right? And those have lithium-ion batteries in them. And if you have bought a phone somewhat recently, I don't know what it depends. Maybe in the United States, at least, I don't know if it's the same in Europe or in Asia or in different regions around the world. But most new phones have like fast charging, so like you might have a charger or a cable that comes with your phone, and when you plug it in, it'll it can say something like fast charging done in 40 minutes or an hour or something. Generally speaking, this is not the best idea, because the faster you charge or discharge a battery, the faster you destroy its life cycle. Battery technology has improved over the years such that this is less of a problem, and it's less of a safety problem than it used to be, but it's still not fully solved. What the calculus, if you will, of this is that consumer electronics like phones, computers, people often like to get new ones because I'm not an Apple person, but the new iPhone comes out feels like every 10 minutes to me. I don't know how often they make new phones or whatever, but they release a new phone or a new device, every year, every whatever, and people want it. And so they get rid of their old device. So if you destroyed the battery life of your phone by fast charging it, and let's say it should have lasted 4 years or 10 years, but because you charged it fast so often, it only lasts a year and a half. Well, the tech companies know that most consumers are going to want to buy a new phone anyway within 9 months or a year. So you've destroyed the battery life, but it doesn't matter because you're getting a new phone anyway, because you want the cool new thing. And so most people are okay with that trade-off. As it relates to your inquiry, you're looking for a big storage system. Probably that is not going to be something that the next Apple iPhone solar voltaic park is coming out, right? So if you were to install a stationary storage system, you probably don't want to be rapidly charging and discharging it to diminish its life, because it's a huge capital investment to apply and make a new battery system if you've discharged it too fast, right? So for a high power delivering kind of system, probably a battery is not the best choice. That's not to say that fuel cells don't also suffer from similar kinds of degradation problems, CO poisoning. There's a lot of things there. But anyway, that's some loose thoughts, I suppose, I can give you on some of those things. There's probably a lot more specific details that you can find in the literature on both technologies, right? Batteries and fuel cells are studied pretty extensively, but from my knowledge base, that's a few things that I can tell you. Let's see. Deeptanshu has asked why we don't get diffusion region in LSV for the hydrogen evolution reaction. Um, that's a good question. I'm trying to find a way to answer this properly. Um, so for the hydrogen evolution, let me share my screen real quick here. Yeah, this is one of those phenomena that happens, and then having to think through why is a bit of a different situation. So, for instance, if you're doing oxygen reduction reaction, you sort of scan and you get this plateau if it's everything's perfect, right? But if you do hydrogen evolution reaction, often you scan negatively, and it just even if you're rotating it, kind of just keeps going down like this. Um, I, some of the answer I think has to do with the fact that you're producing a gas with the hydrogen evolution reaction, right? Uh, H plus an electron gives you H2 gas. Um, and the formation of gas, especially hydrogen gas, which is small, it elutes very, very quickly. Um, I think that that makes it very difficult to form a diffusion layer. You sort of have a similar phenomenon with the oxygen evolution reaction on the other end of the potential spectrum, positive potentials. I think because it's a gas, it might make it difficult for that to occur. The gas is escaping. It also, a lot of the problem with hydrogen evolution, I hear this a lot from people, both OER and HER. It just becomes difficult a lot of times to do, TAFL analyses and different kinds of analyses because the formation of gas on the surface breaks up the electrode electrolyte interface, and it just makes the current data, right, like jump around sometimes. Like, you can get kind of crazy results. So that's another reason why I think sometimes it behaves poorly. Um, I feel like there might be some other sort of auxiliary explanation, something, uh, some other reason that it won't, plateau even if you're rotating, or maybe it does, but it's hard to capture. Um, and to be honest, I would have to probably look myself in the literature a little bit to remind myself some of the answers to that. That's the best answer I can give you now because I think there's a better, maybe a sort of a deeper, higher level explanation from kinetics or something related to it as to why it doesn't exactly plateau all the time. I do think a lot of it has to do with the fact that it's a gaseous formation and the gaseous product, and it won't make a diffusion layer exactly the way like a liquid phase diffusion boundary will. But there might be a deeper answer. It's probably discussed in the scientific literature, uh, and I don't have those answers for you right now. I'd have to probably read a little bit. Um, but in any case, that's the best answer I can give you for now. Let's see. Zaki has a follow up. Thanks for the replies. One last question. How do I find corrosion current electrochemically when the cathodic reaction is in diffusion slash mixed control? You can't, at least not, at least not easily. Um, so what is often done to try to alleviate or get around this problem is to do one of a couple of things. You can scan very slowly. So, like if you're doing a CV or an LSV and you're trying to calculate a corrosion current, that's a kinetic parameter, right? And so your thought process is wise because you're recognizing that finding the corrosion current when I have a diffusional influence is hard because I need to remove diffusional effects because this is a kinetic phenomenon. I think if you one of two things, you're either going to try to do a sweep, for instance, over a narrow potential range, where you're not inducing a huge amount of diffusional effects, or you scan really slowly, like 1 millivolt a second, half a millivolt a second, like painfully slowly, because there's a direct correlation between scan rate and double layer capacitance diffusion non-Faraday processes. Okay. Um, Whereas if you scan very, very slowly, it's kind of like doing a lot of bulk electrolysis processes where at each potential you're sitting there for a long time and you're letting the current decay. And that decay is basically um, letting you're letting the diffusional effects settle, I guess. Um, and so the at least the double layer anyway. So uh, but if you do have a lot of diffusional effects interfering in your like voltammogram, for instance, um, the only way is to deconvolute the data in like a Levitch kind of way where you use some sort of fundamental equations that allow you to isolate diffusion limited current from kinetic current based on the rotation rate and um, you know other constants associated with your system. Um, and beyond that, I mean, honestly, people very often use the current directly from their voltammogram to get kinetic information, either through a Tafel plot or for a corrosion. And in the corrosion field, it's actually quite common to do this. But they partly get away with it for two reasons. One is that they scan very, very slowly, like I said. The other is that in a lot of corrosion systems, there is not a lot of non-Faradaic processes getting in the way. It's pretty it's pretty kinetically, at least observably kinetic behavior is pretty easier. There's not a lot of other stuff going on other than the corrosion. So the assumptions are made that this is an acceptable thing to do. In your case, that might not be what you're observing. You might be very obviously observing some mixed or diffusional control, and then you're either just going to have to try some of the things I said, or take the data anyway. Just do it. Honestly, throw a bit of caution to the wind, um, and you would just sort of note in your explanation or whatever that there's some error here because this is not purely kinetic, but this is the best that I have, so I'm trying to calculate. You would just note that there's some error associated with my measurements. That can also be acceptable, to be honest, but um, that's a good question. Subha has a question. Can explain why we need 3 electrodes setup instead of 2 electrode for electrochemical measurement? You're new to electrochemistry. Please explain, elaborate in a simpler way. Well, I'll try to elaborate in a simpler way if I can. Let's see. So in an electrochemical system, in the way a potentiostat operates, okay, I have, for example, my solution, okay, and let's just say I have my working electrode, right? This is my working electrode, and this is my counter electrode. So this is a nice 2 electrode system. Okay, here's my counter electrode. All right. Now, whatever these are, let's just say this is a platinum wire, and let's say this is copper. I don't know. I'm just making this up, right? Well, the potential, right, uh, of my working electrode, right? The potential is equal to E working. Potential is a relative quantity. It's not an absolute quantity. It kind of is, but let's just pretend it's it's a relative quantity, right? It's the potential with respect to something, right? And so you can imagine the potential that I'm measuring here is with respect to something else. And so when I connect this to my potentiostat, right, on either side of my potentiostat, and I'm running my system, I'm adjusting the potential of my working electrode, my copper or whatever, and it has to be with respect to something. So I have to measure it with respect to the counter electrode, the platinum. Okay. Now, if let's say what I'm trying to study, I think I showed this earlier, right? I showed copper plus 2 electrons. I'm just making up an experiment here, right? Gives me copper, like solid. Okay. And this is, I think it was 337. Let's just say 330 millivolts. So that's the potential associated with this reaction. Okay, let's say this is the reaction I'm trying to study. Well, um, the potential that I measure, I need it to be 300. So I tell my potentiostat, give me 400, right? Millivolts. I want to make sure this reaction occurs in either direction. Right? This is usually equilibrium, either way, whatever. Okay. Well, the potential that I am applying is uh, the copper with respect to the platinum, right? Well, if I want my copper to be plus 300, but my platinum is at 200 because the platinum has its own processes going on. The platinum is in solution. There might be, platinum plus some electrons, or platinum hydrogen, or platinum oxide, or hydroxide. There's something happening with this platinum. I don't know what's going on. It's got any of a number of possible things going on. And so its potential could be who knows what. And then if I start um, doing some kind of redox process at my surface of my platinum, I might be changing the potential all the time. So this potential was 0.2 a minute ago, and now my potential of my platinum is 0.4. Right, it's changing because I've got some processes occurring. I don't know what's going on at the platinum electrode, and so the potential here is now uh, all over the place because it's against something else. And so while I'm trying to get this potential right here, this reference point is changing constantly, or at least if it's not changing constantly, I don't know what it is, right? Uh, and so practically what I would see in my, you know, let's say my voltage versus time plot is my voltage might be moving all over the place. It might be going up, it might be going down, because the reference point is unpredictable. So hopefully this leads you to the conclusion that if I have my reference point all over the place and it makes it unpredictable, if I can get my reference fixed somewhere, it'll allow my working electrode potential to be fixed. And so that's why we use a reference electrode. That's why we need a third electrode here. Okay. And so what we do with this reference electrode is we pick something in here, like silver chloride, for instance. So Ag plus Cl minus, um, Ag plus Cl minus gives me AgCl plus an electron. Okay, so this electrochemical redox process, for instance, has a potential associated with it of 200. It's like what is it, 220 or something? 200 millivolts. Okay. Now, unlike platinum, what I talked about before, where this could be moving, this could be something different. It could move around. Platinum could be making hydrogen or oxides or hydroxides or something. This redox reaction, if I have silver chloride with KCl and I have a specific redox species, is not going anywhere. It's fixed. It's stuck. It's there. It won't change. And so what I do is my potentiostat operates in such a way that it measures the potential only between these two, not here. It does not measure the potential with the counter electrode. So the potential is adjusted between my copper, my working electrode in this case, and my fixed reference electrode, right? And so whatever my potential is that I measure or I tell it to measure, right, is against something that's steady and stable. And so I know with relatively high certainty that the potential at my copper electrode is the value that I'm looking for instance, because what it's measured against is not moving. Okay. And so that's without getting much more technical. Again, I know you asked it for a simpler way. There's a lot of potentiostat operation and things like that, that I don't want to get too heavily into. But generally speaking, this is why we're using a 3-electrode setup, because we need to know the specific potential of the thing that we're studying. And if it's against something that's moving around, well, then its potential is also moving around, and we can't be sure what process is occurring, because the process that's occurring on my working electrode is a function of the potential that it's at, right? And if the potential it's at is moving around everywhere, then we don't know what's happening. But if we do know where the potential's at, we can be more sure what's happening. And so that's why you use a reference electrode. That's why you need a 3-electrode system. All right, where are we at here? So, okay, let's see. Olshas has a question. What do you think of the current state of hard carbon anodes for SI? Is that silicon ion battery? What's SIBs? Sodium ion. Sodium ion. That's silicon. Hard carbon anodes for sodium ion batteries. I've heard that they're poorly studied. The sodium, yeah, Na plus, of course, Na plus. Sodium storage mechanism, to be particular, what would you say? That's a good question. So I'm not familiar with this. I've studied lithium ion batteries, and with lithium ion batteries, carbon is typically used as the anode. For a lithium ion battery, I'm actually not sure. Is carbon used more regularly for sodium ion batteries also? I know that for lithium, for example, carbon is a good anode, um, for lithium ion batteries, because lithium intercalates well into carbon, into the lattice, into the structure, and so it's a good storage mechanism. Um, excuse me, for lithium. It might behave similarly for sodium, and I'm not positive. I also don't know hard carbon. What is that? What is that? What does that descriptor mean? So the only thing that comes to mind for me, for instance, is that one of the kind of interesting phenomena. Again, I can speak for lithium because that's what I studied when I was in graduate school and as a postdoc. Is sort of counterintuitively the carbon that's used for the anodes of lithium ion batteries must have a very low specific surface area, not high. Most of the time, for most electrochemical systems, people are trying to increase the specific surface area, like how many meters squared per gram it has. And you know, to increasing the surface area, increasing the electrocatalytic activity, all that kind of stuff is pretty common. For batteries, however, it is the opposite. A very high surface area carbon performs very poorly as an anode material. So I only bring all that up to say that I wonder if the term hard carbon that you're referring to is sort of a um, what it means is that it's like a carbon with a very low specific surface area. That's what it makes me think of. Um, and if all of that is the case, then I would say probably it's something that could work if sodium stores and intercalates in a similar fashion to lithium. I do think probably it is a little more poorly studied, and that's mainly because lithium is the state of the art for the most part. I know there are some people who do study sodium ion, and speak for it pretty highly, and are trying to find ways to commercialize it and provide an alternative mechanism for batteries to lithium, which is always a good thing. That's what the scientific endeavors are all about, right? Trying to find the next state of the art and alternative ways of using our discovering energy. Um, um, that's as much as I can say about that because I don't specifically have a lot of knowledge of this topic. But again, it's more I know to a certain extent about the surface area issue with related to lithium, and I guess my assumption would be that this, without any other information or having studied it, is that this hard carbon might have something to do with that. Um, and yeah, I hope it does become more heavily studied because I think it could help fill out the 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 field of knowledge we have of these different battery technologies. Let's see. Salman has a question. What type of electrochemical cells are most employed in industry for practical applications, and what should an academic researcher expect before going into industry? It depends what industry, obviously. What kind of electrochemical cells are most employed in industry? Batteries, probably at the moment. Um, Batteries take multiple forms: coin cells, pouch cells, prismatic cells. Those are similar, pouch and prismatic, and cylindrical cells. Um, so if you're in battery technology, electrochemical battery research of some type, um, those are helpful and useful. If you're going into a battery industry, studying how they're constructed, the cylindrical cells, jelly is called the jelly roll. It's a rolled up kind of a thing. Coin cells like a sandwich. So is prismatic cells and pouch cells, but it's like a lot of sandwiches all stacked together. Otherwise, I would say that to a certain extent, your question is not. Um, it's not something you need to be terribly concerned about. And what I mean is, as a researcher in academia, if you're studying, for instance, a small liquid cell with 3 electrodes and you're doing voltammetry or something, and maybe that small form factor, system is not exactly used in industries or companies or large scale industries, I would not approach your research time as looking at that and saying this is a waste of time because they don't use it in industry. Um, that isn't probably a helpful way to go about thinking that through. And the reason is that the phenomena and the electrochemistry knowledge and the processes that you're going to learn from a small system, they might not all exactly scale to an industrial process, but the fundamental knowledge that you're going to learn in academia working with this type of electrochemical cell or that type of electrochemical cell, those phenomena and processes and that knowledge you're going to learn will be useful. I'm in industry now, and I did, many years in academia as a postdoc and everything as well. And I have found that I was able to adapt a lot of my knowledge of those kinds of small cells and systems. As well, my company specifically uses some of those. We're not like a research company. So, like my industry in particular, my company isn't necessarily the exact kind of thing, right? We're not doing electrochemistry R&D to make a better. We're developing the equipment that people use to do that, right? So it's like a different kind of phenomenon. But like for example, if our if my company is testing uh, a new reference electrode, and we develop a new product which we do, right? I develop a new cell or I develop a new electrode. Well, I have to test it to make sure that it's working properly. I have to run some diagnostics on it. And a lot of those times, I'm using the same kinds of cells in the systems that I studied in academia. So there definitely is still some crossover, in addition to just, like I said, the knowledge of that you're using. So I wouldn't necessarily approach your research career in this way. Is my advice. Don't think that I'm wasting my time using such and such a cell because they don't use that at this large industrial company. You're still learning and gaining valuable insight, and you will be able to extend your knowledge of those principles to the new system that you're working on. And honestly, in many cases, it's just simply impossible to use the practical industrial setup while you're in academia. The only way to do that is to get an internship at that company and see their system for real. Because in a lot of cases, like some company that's doing large scale industrial processes, whatever it is, they have their own equipment, and like the academic the university or whatever does not have that equipment. You simply can't gain the experience unless you find a way to, again, have some sort of internship or get a job at this company. So I don't want to I guess I'd say I wouldn't want to proliferate the idea that working with academic sized or smaller systems is not useful because it's not what they use in industry. That's not really exactly the case. All right, moving on here. I'm trying to get through. We're getting close to the end of our time, but I'll try to get through everything, of course. Let's see. Rajan has a question. On a pine carbon rotating disc electrode, if the thin film coating is not good enough, what strategy would you suggest to get a fine reproducible film? Polishing electrode or checking the catalyst ink? For sure, part of this process is polishing the electrode. The method that I like to do for reproducibility is to, for example, the polishing, let me just pull up a website. I can kind of talk through it as well. See if I get the polishing. So polishing, share this slide. So this is like a polishing kit that we sell. You'll find similar sorts of polishing materials depending whether you buy them from Pine or from anybody else. But you have these white discs. These are nylon, and then up here is the top one is like the cloth, and you'll have 2 or 3 different solutions. So you see 5 micron, 0.3, and 0.05. Okay, so I just wanted to kind of bring that up very briefly, right? So the method that I liked to use is I would use the middle or the biggest alumina. So again, 0.3 or 1 or 5, something like that, with the nylon pad. I always use that first after finishing an experiment. So the first thing that I do is I use the like coarsest. It's not like sandpaper, right? It's not going to destroy your electrode or anything. But because it's nylon and it's the biggest particles, it's most likely to wipe the old stuff away from the surface. And so I would do that for not that much time, maybe a couple of minutes at most or something. But the first strategy being I'm wiping away my old ink as much as I can. Then I would rinse my disc, right? Rinse it pretty well with water, acetone, whatever, and then do another polish with the microcloth and the fine. Okay, so that order hopefully will do a good enough job of wiping away my old film. And because it's a 2-step process, if you just do a 1-step polishing process, I always caution against this, because if you get your pad, you put your slurry and you start polishing your disc, you have slurry and some water, and you have the film, and it's wiping it off the surface. But where is it going? It's going into the slurry, right? So you are polishing with the remains of your old film. Is it going to re-stick on the surface? Maybe, maybe not. Hard to know. So if you have 2 steps, use a different place on the same pad or a different polishing pad altogether, a fresh amount of alumina, you decrease the likelihood that any of your old film will still be there. So that's the first thing that I suggest. Okay. The second is to run electrochemistry test after that process, always on the blank glassy carbon, just in acid, whatever. And you should get a plain looking CV with nothing. Like if your film is platinum or something and you get platinum peaks, always run a blank CV before you try to make the new film. Because if you see any residual stuff, do the polishing step again. Do it again, see what happens. You should restore the fresh carbon surface between each one of them. And then the last bit of this is related to the reproducibility. There's a lot of strategies related to that. I always like to plug my my friend Yannick Garcini. I'll try to pull up a paper. My friend Yannick Garcini from the Naval Research Laboratory. I think this paper I have cited to people. I'm gonna share this screen with you. This is a paper. He has done a tremendous amount of work. He's one of the only people I know, and there may be more. I like him. He's a friend of mine, and I'm going to plug him anytime I can. He's Yannick Garcini. This is his name. Again, he's at the Naval Research Laboratory in Washington, D.C. And you can see standardizing thin film. He's done a tremendous amount of work. I don't know if this is the full article. Yeah, it doesn't look like it is. He's done a tremendous amount of work qualifying and quantifying the film that you make on a glassy carbon disc, for instance, and how it affects your results, specifically with platinum and carbon. So this is a thin film formation paper. I'm going to put the DOI into the chat so you can check out that paper if you want to. There's a lot there. I can talk very briefly about it so I can move on, but basically there's a lot of strategies that you will probably want to work on with your ink to get a reproducible film. A lot of it has to do with the ratio of your active material to your solvent, what the solvent is. Is it water? Is it alcohol? Is it water and alcohol? Water makes a nice film, a nice bubble on the glassy carbon surface. Water is has a higher surface tension, especially if you have a Teflon shroud. It won't spread. Teflon is very hydrophobic. But alcohol has a lower or higher. Like water makes a nice bubble. Alcohol makes a more flat bubble. So alcohol is more likely to spread over your shroud. That can affect the reproducibility of your film. How much binder you use in your ink can affect how the film coats. Sometimes you do a 2-step process. You put your film, dry it, then put a Nafion suspension on top to glue it as a binder in place. That's what I used to do. I used to do a 2-step process. Some people combine it as one. How you dry it, usually spinning while you dry the electrode upside down, can help improve reproducibility. It depends on how well your catalyst material dissolves in not dissolves, but mixes in the ink. If it's not mixing very well, your loading will be unknown. There's a lot there, right? I encourage you to look through some of that publication that I linked, as well as anything else by Yannick, and practice. It's just practice. Practice over and over again on making that film will help your reproducibility. But the polishing step that I talked through will hopefully help you too, because if you get the film super well reproducible, but you're not wiping away the old one in between each step, well, then it's irrelevant, right? Because you're going to have old film and new film talking to each other, and you'll never be able to know whether your results are valid or not. Okay, let's see. Next, BGMI Shorts. This is how to select the potential window for a CV measurement. So Mainly the answer is trial and error. A more complicated answer is to look into the literature, see what people are doing, and to look at the things that the type of redox processes you're trying to study. So, for example, uh, one way, without knowing anything or doing any of those kind of study that you want, if you're trying to do a voltammogram, I versus E, you can pick. You're just going to basically slowly work your way to widening the potential. As the most common example in water, you typically have about a 1 to 2 volt window. It depends on the catalyst and a lot of other things. At the extreme negative potential, you have the hydrogen evolution reaction. That's basically ripping apart water to form hydrogen gas. And at the extreme positive end, you have the oxygen evolution reaction, which is ripping apart water to form oxygen gas. Those are basically defining the limits, like overall potential window of your solvent. If you're trying to study a particular redox species, you want to probably focus your potential window around the potential at which your redox process is occurring. So if you have some redox process that occurs at these potentials, well, you probably want to limit your potential window to here, right? Um, but if you're trying to capture more behavior, you can start here, right? You can then increase your window a little bit on the positive end, a little bit on the negative end, and you might, the drawing not being the best, just don't worry about it. I'm not a great artist, but you might do that. And you might say, okay, and then I could increase it a little bit on both ends again. And so you sort of do this progressively. You do 100 millivolts at a time, 200 millivolts at a time. And eventually you might end up with some, kind of a thing where you end up on that end. This peak shouldn't be getting bigger. I'm just a bad artist and I'm trying to make it so you can tell the difference. Um, and then maybe on this end, it starts to go up like that, right? So this right here, as I said before, this is the hydrogen evolution reaction. If this is water, this right here is the oxygen evolution reaction. Those might be indications that, okay, this is like, I shouldn't go any more negative than this, and I shouldn't go any more positive than this. And so, like, these would be your limits of my potential window. On the other hand, you might not even want to go anywhere near the HER because you might be overly reducing something. So you might want to cut it off here. Maybe you should cut it off here. And you don't want to go any more positive, so you would cut it off here. Maybe you want to limit your potential window even more because I basically want to capture this peak behavior plus a little bit more on either end so I can resolve the data. But I I'm happy with that. I don't need to go much more positive. And a lot of times this determination is done so that it's relatively symmetrical. Like if I do my CV and I get, something like this, it's like I have all this extra, you know, on the left and like nothing on the right. A lot of times people won't do this because it's just ugly. So you'll try to get like an equal amount of like, you know, tail on the left and the right so that it's centered. So a lot of times it's cosmetic, to be honest, where you're setting your potential window. So those kinds of things go into the equation too. But a lot of times it's really trial and error, and you can slowly increase your window little by little until you really qualify where you're trying to study. But that's the best, probably the best practical way to do it. It looks like there's a follow-up question or statement here. Here, using silver chloride as reference, platinum as counter, sodium sulfate as the electrolyte. I'm confused how to select the potential window and what will happen if you see. Okay, so yeah, so everything I just talked through is hopefully an answer to what you're talking about here. What will happen if you exceed the potential window? If you only exceed the potential window by a little bit, you're just going to do more of the oxygen evolution reaction at the positive end. or the hydrogen evolution reaction at the negative end. If you really, really greatly exceed the potential window, you could run into some problems. For example, if you have a glassy carbon, whatever, working electrode, and you go way too positive a potential, you will oxidize the carbon electrode itself, and you could damage it permanently. Okay, so you want to be careful, and you could have similar problems if you go too far negative. Almost for sure, you're not going to damage the reference electrode. Almost for sure, you're not going to damage the platinum counter electrode. But your working electrode is one that could get in trouble if you really greatly exceed the potential window. But if you do scan too far positively by some moderate amount and your current goes up, you're just doing oxygen evolution reaction. Pull it back, run it again. You're probably not causing too much problem. I'm talking about if you go like a volt too high, or a volt too low, or 700 millivolts too high or too low. You could start getting into some problems. So you want to very sort of carefully or gently increase the limits up or down to avoid, just incautiously saying, let's just go plus or minus 2 volts and see what happens. That could damage your electrode. So try to do it a little bit at a time, and you'll probably be okay. All right, looks like there's I'll try to get through these questions. There's a few more here. Rusty has a question. Why is there a hysteresis of LFP material in a graph, E versus lithium content, when GITT analysis is performed? Yeah, so this is the hysteresis and the charging. Well, whether it's lithium iron phosphate or anything in particular, the hysteresis is a very odd phenomenon. And so if for those who don't know what we're talking about, basically it's as you charge a battery up, I wanted to pull, I had a, there's a paper I found that had a good, that's not the one. I'm trying to find this. Let's see if there's a plot that I can kind of show. Yeah, this might be an okay explanation, so I don't have to draw something and use my absolutely terrible artistic ability. Okay, hang on one second. I'm just gonna cycling. So hopefully you can see this. Yes. Okay. So when you're charging and when you're discharging, whether you're doing GITT, which again, for those who aren't aware, galvanostatic, GITT is galvanostatic intermittent titration. Test, I guess, what's the second T? Galvanostatic intermittent titration. Yeah, I guess it's I don't know. It's a good question. Galvanostatic. Now I'm curious. Hang on one second. Intermittent titration. I don't know what the second T means. That's a good question. Anyway, sorry, I'm getting a little distracted here. In any case, it's a test where you charge, you release at OCP, charge, release at OCP, charge. You do that progressively until you get all the way up. Whether it's a GITT test or it's just a straight galvanostatic charge discharge, you often get this hysteresis. And so what you're seeing is this here. And if don't worry about the specifics of this paper here. Effectively, it's as I charge it up or down or whatever, I have this blue curve, and then as I go the other direction, I have this other curve. And so there's a difference in the voltage that I get depending on the state of charge, depending on which direction I'm going. It's a very weird phenomenon, and you'll find some. So, for example, you can find. So for example, one of the explanations they give, hysteresis results from thermodynamic and tropic effects, mechanical stress, microscopic distortions within the active material particles. It's a weird answer, right? to sort of, I don't know, translate this into common words, from the best of what I can tell, there is not a very obvious explanation for this phenomenon. I think one of the ways that I tend to describe it is that there are some, well, first of all, there's some IR effects, IR drop, depending on whether you're charging up or charging down, that impacts the exact voltage you're reading at any time. And I described earlier in this live stream, so apologies if you didn't see my explanation, but I talked about the voltage of a battery at any time is the voltage of the cathode minus the voltage of the anode. Okay, and the at any particular lithium percentage in both the anode and the cathode, the voltage of your battery is the difference of those two, and whether you're charging up or charging down, there is there might be a different how do I put it, a different sort of even though it's the same lithium percentage, it might have a different mechanistic phenomenon whether it lost the lithium or gained the lithium. So like if you gain 20% lithium or you lose 80% lithium and you get to the same place, the structure mechanistically of how that occurs might differ depending on which direction you're going. And so the voltage difference that you measure is slightly off. My other interpretation, and you'll read some papers, you'll see a similar kind of explanation. This mechanical stress distortions within the active material. It's a similar phenomenon to what I said. The physically insertion or deinsertion of lithium is a little bit varying, and it just causes the voltage to be slightly different. I don't want to be too cynical here, but my other impression of this, based on that kind of explanation, is that to some degree, nobody really knows why that hysteresis forms, and I think that's largely true. When I see my impression of explanations like this are somewhat well, I shouldn't say somewhat. They're intelligent methods of trying to explain a phenomenon that we observe, but for the most part, we're not entirely sure. Right? There's stresses and distortions and things, and it's like we're not really sure why something happens. So there might just be some heterogeneities and non-uniform processes. It's kind of I'm being a little overly cynical. I acknowledge that, and someone might correct me and say, actually, we've observed this phenomenon, and that might be the case. But my impression of this, to be perfectly honest, is that it's sort of like we're not entirely sure, so we're just going to make up some things. It's kind of like how I've talked about in the past. If you've ever joined me in this live stream, people ask, what is a CPE? What does the alpha mean? And my answer is sort of, well, it's a heterogeneity of the surface. It's the same thing. I'm making it up to a certain extent. We observe an odd phenomenon, right? This is like engineering 101. It's like we observe some physical phenomenon. It's a bit odd. It's a bit weird. Theory dictates this is what it should be. Practicality and empirically, we observe something a little different. So if we just add an exponent, if we just hand wave and say, oh, there's some stresses, there's some non-ideal behavior, there's some other things, then that accounts for why we see what we see. The hysteresis and a charge discharge of a battery is, to me, one of those kinds of things. It's just kind of this odd phenomenon. It's a stress thing. It's a bit of a oddity of the insertion process, deinsertion process. It's an IR drop. There's a number of ways that might be describing of it, but that's the best that I can kind of provide you from my knowledge of it. And again, to a large extent, I really think the answer is that we don't 100% know. Let's see here. Tarek has asked, can I explain Kramers-Kronig transform in more detail? Can it be applied to any EIS data set? Are there any specific conditions that need to be met? No, it can be applied to any data set. I can show you. Let me pull up these slides. Try to describe Kramers-Kronig. So there's two aspects of Kramers-Kronig that are relevant, I would say. This one here. So Kramers-Kronig, strictly speaking, is mathematical. As it relates to impedance, it is there's other parts of it, but it's this equation. I'm just moving these circles out of the way so you can see. So they're part of my presentation here, the webinar. Basically, these two equations are the Kramers-Kronig relations. Okay, they're just mathematical descriptions, and so we have the real impedance. We have as a function of frequency is equal to the infinite frequency resistance, which is like the IR drop, times constant times the integral from 0 to infinity frequency of this this integral. This is, I mean, again, it's just a mathematical relationship. I mean, it relates the real impedance to the imaginary impedance as a function of a frequency, and then there's a similar imaginary imaginary impedance as a function of the real impedance, and basically the way they relate to each other mathematically is the essence of the Kramers-Kronig relations. Any more in-depth explanation would probably require, to be honest, diving into the papers that Kramers and Kronig wrote in the 1960s, 70s. I don't remember the exact time. The application of them comes from the 1980s, 1985, I believe, where a researcher in the Netherlands or Denmark, somewhere in Scandinavia, I think. And so my apologies to Dr. Buchamp, who developed the technique to practically apply the Kramers-Kronig relations. Because the problem with the Kramers-Kronig relations are that you need the infinite frequency resistance, which is impossible because we can't measure anything at infinite frequency. We can substitute with high frequency, but it's not exactly the same. We also cannot perform anything at 0 hertz. That doesn't even really mean anything. And we can't perform anything at infinite hertz because we're limited by potentiostats. Basically, we can't analytically apply the Kramers-Kronig relations very easily because it's a sort of an infinite mathematical integral and everything. We're limited by that. So what we do is we use this transitive property, right? We pick a circuit. If a circuit satisfies Kramers-Kronig and the circuit satisfies our experimental data, then if A is B and B is C, A is C. And so our data satisfies Kramers-Kronig. And so basically that is what Dr. Buchamp proposed, I guess at this point about almost 40 years ago, and has been used, to my knowledge, by every manufacturer and Kramers-Kronig algorithm, my company included, is that we fit this sort of infinite sum of resistors and capacitors and Randall's elements and an inductor, and this circuit satisfies Kramers-Kronig necessarily because every ideal component by itself satisfies Kramers-Kronig, as well as any combination of those circuits also necessarily satisfies Kramers-Kronig. So in some respect, it is like a very convoluted circuit fit. But what it really is finding a way to fit the most like nth order polynomial to your data. And if it fits, then it presumes that Kramers-Kronig is upheld, or at least valid. And the specific conditions to be met are the conditions of stability, causality, and linearity of your system. And so what is hard with Kramers-Kronig is that if it doesn't fit your data, it means one of these or more are violated, but it doesn't tell you which one. It just tells you that it's not valid. So it's not exactly an identifier of which of them. It doesn't have that ability. But yes, for the most part, it can be applied to any EIS data set. You can apply this, and if not just EIS, any impedance, because impedance is not just electrochemical. Impedance is sort of generally any data whereby an applied sinusoidal input gave a sinusoidal output. That's impedance, all of it, right? It could be electrochemistry with potential and current, or it could be anything else. So there's a decent overview of Kramers-Kronig for you. And I think I'll have the last question here, and then we'll call it a day and a weekend and everything, is from Joshua, who says, "Hi, I'm trying to build a galvanic cell at home. Uh-oh, it could be dangerous. Using aluminum as anode, solution of potassium, aluminum sulfate. And for the cathode, I'll be using copper in a solution of copper sulfate. Pentahydrate. Should this work? Potassium, aluminum sulfate. So good question. At home. So the key to this is going to be the reduction potentials that you have. So you have an aluminum and copper cathode. Let me just take a look real quick here. So I'll try to figure this out with you on the fly because I don't know. I suspect it will work. Standard reductions. Let's just take a look at some potentials, shall we? So if the aluminum's the anode and copper is the cathode, so our copper, where is it? Probably over here somewhere, right? Copper. So let's just say this is the copper. I think the other one I had was 300. Yeah, 340. So the cathode is, this is the potential of the cathode, and you're going to subtract the potential of the anode, which is aluminum. So presumably that'll be down here somewhere. Aluminum 3 plus is minus 1.6. It's quite a large potential. So in theory, your cell potential is going to be the cathode minus the anode, which is going to be 300 minus a minus 1 point whatever. So you might have 2 volts of potential, and what you'll be doing, I suppose, if you connect this to some sort of a load where you can lower the voltage and get energy from it, is I suppose you'd be dissolving the aluminum, because the aluminum is the anode, so it's going to do the other way. So aluminum solid will go to Al plus 3, and where's the copper? I went past it. It's over here. Your copper, nope, not that one. 3, probably the 2 plus reaction is my guess, but your copper will be, you'll be adding copper to plating more copper onto the copper electrode, basically, and so you have copper sulfate solution. Potassium aluminum sulfate. In theory, this should work, I think. I think in practice, you will just have to try and see what happens. You'll need some sort of separator. I don't know what you're going to have between the two. Like, you could do something as simple as having, like I remember in high school or something like that, we'd do galvanic cells. Usually it was like zinc and copper. and you have 2 cups and you could even just put a paper towel in between. It's kind of silly, but that allows for the ions to transfer between the two. For you, if you have it as you might sometimes you can soak some sort of porous material and sandwich it between the two anode and cathode, connect to it somehow electrically, and you can run it that way. With batteries or with galvanic cells like this, it often depends, because if you have it as a big solution with the 2 things sticking in solution, you have diffusion that can slow things down, make it troublesome. So while that's the voltage you should get, you might not get a lot of current because diffusion is killing it. So if you push everything together closer, you're limiting diffusion. The distance is smaller, and so you might get more current out of it. In theory, though, just based on the thermodynamics of typical, half reactions, I think that should work. So I hope you have good success with that. Feel free to report back either in a comment or come back to one of our future live streams and tell us how it went. I'd be curious to know. Please be safe. Copper and aluminum aren't terribly dangerous, of course. In general, copper sulfate's pretty benign for the most part, but I would just be remiss if I didn't say please be safe if you're doing homemade chemistry. I've certainly done some myself, but we always want to make sure we're cautious and being safe, because you can always have unwanted things happening, etc. So please do be safe. Well, I'm going to wrap it up here for the week. My colleague Alex, as I said at the top, is not with me today. He may be back next week. I will not be here next week with you, which would be June 7th. After that, it gets a little bit hairy. Just so everybody's aware, as June and July and August in the summertime, both Alex and I have various times where we will be out, one of us or both of us. So we will do our best to continue doing these live streams, but don't be surprised if there's a week or so that goes by where we're not around, so you don't see us. We haven't forgotten about all of you, and we will do our best to keep coming back, in the weeks that we're around. But until then, I hope everybody had a good time, and I hope I satisfactorily answered your questions. Have a good weekend, everybody. Thank you all very much for your engagement. I do appreciate it. And have a great weekend and week ahead. Take care, everybody.